Hi guys, we're going to tackle the last two sections in chapter 3. We're skipping a couple of sections because um, it's just an 8-week class and there's a lot of material in this unit. Please, I beg you, do your homework. You're not going to pass this test without practice. So, 3.8 is all about implicit differentiation. Okay. Um, Derivatives that we've done so far, we have been given f of x or y as a function of x, and then we take the derivative, also notation, the derivative of y that depends on x. I haven't been using this notation much just because it means the same thing as y prime, but it's very important now that we get comfortable with this notation. And you'll hear me explain this again when we get to chapter 4. But with what we're doing right now, it's very important that we use the dy dx notation. This says explicitly that y is a function of x. Okay? So we have had an explicit relationship here between the y value and the x values. Y is dependent on x. X is the independent variable. We've just assumed that that was the case all along. Sometimes y is a function of time. Sometimes x is a function of time. Sometimes x is a function of y. Sometimes x and y are independent of each other, but they both depend on time. We'll be doing all kinds of problems that are like that in the next two sections. But when you see this notation right here, you know that y is a function of the variable x. And it's usually written y equals, but not always. And that's the point. In this case, it's explicit that y depends on x. And we can take that derivative and we get y prime is a new function of just x. But now we're going to have situations where the x and the y are in the same equation and they're all mixed up. Sometimes they're even multiplying each other. Sometimes it's hard to extract the y value and rewrite as y equals. We can do it in this case, but we would get y equals plus or minus the square root of 4 minus x squared. You see that this is not a function because you have two different y values for every x. So it ceases to be a function, and that causes problems. But if we take the derivative with this format, we're going to have the plus or minus in it. Then we're going to be multiplying that by a minus when we take the derivative of the inside. And this is really nasty, where this is actually quite easy. We're going to get the same answer, but because our equation started out as just implied that y is a function of x, and the reason that it's implied is because we're told to find dy dx. Because those are our instructions, we know that y is dependent on the x value. So here's how we do an implicit derivative. It means it's just implied that y is a function of x. We're just going to take the derivative of this equation term by term, and then when we take the derivative of y, we have to chain rule. Why? Because y equals all of this stuff. So we have to take the derivative of the stuff inside the y. And I know that sounds ew, but it really isn't because it's implied. So here we go. The derivative of x squared is 2x. The derivative of x is just 1 because we're shown in the directions that x is the independent variable. So in this case, he's just 1. We could say his derivative is dx, and we'll work the problem that way soon. But for now when we take the derivative of y squared, it's 2y, except that all of this stuff is inside the y, so we have to chain rule the derivative of y with respect to x. And we have an equation here, so we have to take the derivative of both sides of the equation, and the derivative of 4 is 0. And now, since the directions tell us to find dy dx, I have this equation with a dy dx in it. I have to isolate this guy. So I'm going to subtract the 2x from both sides. And then I'm going to divide away the 2y. So I'm solving for dy dx, and that's going to equal minus 2x over 2y. But then I simplify, always reduce your fractions to lowest terms, guys. Dy dx equals minus x over y. And you notice that now my implicit derivative is also implicit. It's got the y inside of it. And that's okay. You don't have to replace the y with all of this stuff. Now, if you took the derivative of this as it is, this is blob to the half, you would bring down the half and multiply. Remember, it's plus or minus. This blob would be to the minus 1/2, and then you would multiply by negative 2x. Well, the 1/2 and the 2 will cancel. The negative will make this minus or plus. I know it's awful. But then you would have x on top and the square root on the bottom, minus x on, well, this flips over. Let's not flip it. Let's leave that. Have minus x on the top and the square root on the bottom. Well, look, y equals plus or minus the square root on the bottom, and there's your minus x on the top. So they're actually the same exact answer. Let's try another one, maybe with a product rule in it. Okay, let's say that we have x squared plus y squared minus 3x plus 2y minus 4x times y plus 3 equals 0. Now, take the derivative of each term, and anytime you have a y, you have to chain rule out the dy dx. So we're going to get, hold the phone, find dy dx. That tells you that y is actually a function of x. It's hard to extract from here. It's doable in this case, but ew, you don't want to have to do it. So we're just going to take the derivative as it is, and wherever we end up with the dy dx, we will solve for the dy dx in terms of all the rest of it. Okay, so first things first. The x squared gives me a 2x, y squared gives me 2y, chain rule the dy dx. The next term, minus 3x, gives me a minus 3. The next term, 2y, gives me plus 2, derivative of y. Now, the next piece is going to be a product rule. You see that we have 4x times y with a minus on the outside. So I'm going to choose to keep the minus 4 on the outside and do the product rule xy on the inside. So product rule says derivative of the first, which is 1, times the second, plus the first times the derivative of the second. So that's the derivative of xy. plus the derivative of 3, which is 0, equals the derivative of 0, which is 0. All right, I'm going to distribute that minus 4. And I don't really care about the y's at this point. It's the dy dx that I care about. I want to get all of my dy dx pieces together and then factor out the dy dx. So how many dy dx's do we have? We have 2y plus 2 minus 4x. And now the other bits, and equals 0. So now all I have to do is move this stuff over to the other side and then divide away the stuff I don't want. So I'm going to get dy dx equals, I'm going to add 4y, add 3, subtract 2x, and then I'm going to divide away the 2y plus 2 minus 4x, and I am done. Some of the problems in the homework may ask you to plug in value for x and y, something like that. But this is the important part, just being able to take the derivative and then solve for the derivative itself. Let's do one more example. Let's say that e to the minus 3x times x squared plus y squared equals 4. Okay, maybe we'll do more than one example. Find dy dx. So we have a product on the left-hand side. So I'm going to take the derivative of the first, and it's a function of x alone times the second plus the first times the derivative of the second, which is 2x plus 2y dy dx. And there's my only dy dx in the whole problem, equals the derivative of 4. So first things first, this is the guy I need to isolate. So I'm going to distribute this through here. Then I'm going to take anything that doesn't have a dy dx and move it to the other side of the equal sign. And then I'll just divide by the 2y. So we have minus 3 e to the minus 3x times the blob. Then I'm going to have plus 2x e to the minus 3x plus 2y e to the minus 3x dy dx equals 0. All I did was distribute the e to the power. All right, this is the bit I want to keep on the left. All of this stuff gets moved over to the right-hand side. So I have 2y e to the power dy dx equals positive 3 e to the minus 3x blob minus 2x e to the minus 3x. Now you see there's only two terms there, and they both have an e to the minus 3x, which I'm going to factor out because when I divide, I'm going to have that in my denominator. Right? So on the top, I'm going to factor out e to the minus 3x. And now, right here, I've factored this out. So I'm going to take that 3 and distribute it. You'll see why in a second. So 3x squared plus 3y squared, and then minus 2x, bang, bang. And my final answer, I'm going to make the top look pretty. 3x squared, no I'm not, I'm going to leave it exactly like it is. It's neat enough. Nothing can be factored, so let's just leave it. And there is my final answer. Isn't it cool how the e to the minus 3x is just completely gone? Very quickly, if you look at the original problem, this could have been written like that. Now, if we take the derivative in this form right here, hold on, I want to give some room so we can, so I can show you something. If we take the derivative this way, don't forget to chain rule your y every time, equals 12e to the 3x. Notice that when I solve for dy dx here, I get 12e to the 3x minus 2x divided by 2y. Now, we can't have different answers. We should get the same answer working it both ways. So I want to show you something real quick just because it's interesting. And I don't want you to be confused. 12e to the 3x minus 2x over 2y has to equal 3x squared plus 3y squared minus 2x. Sorry, I'm on the edge here and I can't write. Hold on. To minus 2x divided by 2y. Well, these two y's are the same, right? They'll kind of cancel out and we'll be left with the tops. Well, both of these tops have minus 2x, so those can cancel out. So now look at what we have. We have 12 e to the 3x equals 3x squared plus 3y squared. Is that true? Well, let's factor out a 3. We're left with 4 e to the 3x equals x squared plus y squared, which is what we started with right here. So you see those answers are actually equivalent. That's the tricky thing about an implicit situation. So I find this stuff lots of fun. You may think I'm weird, but okay, I'll take it. Either form of the answer would be correct, but because the question was given in this format, this is the better format for your answer. Okay, moving on to 3.9. Okay, the reason that we need implicit derivatives is because sometimes there are actual situations where y doesn't depend on x, and x and y both maybe depend on time, for example. X squared plus y squared equals 10. Watch this. What if I want to find dx dt? when, let's say, x equals 5 and dy dt equals 3. Just making up some random numbers here. What happens in this problem is the way the question is asked. You see that x is a function of time, and I'm going to assume in all of the problems you're going to do, y will also be a function of time. So there's a situation here that's changing through time, and the x and the y don't depend on each other, but they both depend on how far into the situation we've gotten. They depend on time. So we're going to take the derivative the same as we did before, 2x, but now x is a function of time, so we chain rule, plus 2y, but y is a function of time as well, right? Because we're given the value of the derivative of y with respect to time. Equals the derivative of 10 is always 0. So now let's look at what we need. We want to solve for dx dt, and then we're going to plug in values for the x and the dy dt and see what we get. So dx dt will equal minus 2y dy dt divided by 2x. And I'm just going to simplify really quickly. Not much, just basic simplification. So I'm going to get minus y over x and a dy dt multiplying. So let's plug in what we know. Dx dt, the x is 5. This is given in the question. Dy dt is 3. But we have an issue. We need to know what the y value is, because that wasn't given. Or was it? With these problems, there will always be some kind of constraint. You're going to have to take the things that are given, this stuff, and the original equation to find the missing piece. We're given everything that we need to know. So let's go back up to the beginning and say that x is 5. So y squared is going to be 10. Hold the phone. You didn't see that. Backing up. That's 100. How's that? Fix that problem. I was going to end up with a complex number. So 100 minus 5 squared gives me 75. Take the square root of that. And in this situation, because most of these things are, we need to know the situation to know whether it's plus or minus. So I'm just going to put plus or minus. Square root of 75 is the square root of 25 times the square root of 3. And now I can plug that guy into my answer here, plus or minus 5 root 3, and I'm going to get plus or minus 3 square roots of 3 for my rate of change of x with respect to time. Now, what kind of situation could this be looking at? Let me show you. This is called related rates, is what it's called. And we're in 3.8. 3.9. Let me write that down. This is 3.9 related rates. And I think your homework assignment was on the front page. Here's the situation. Let's use the same type of setup here. Let's say I have a house. Don't laugh at my house. And there's a ladder leaning against the wall. Let's say that the ladder is for 13 feet. Let's also say that the base of the ladder is being pulled away from the wall at something like 3 feet per second. What's going to happen to the ladder? Well, if the base is being pulled away, the length of the ladder isn't going to change. But the top of the ladder is going to fall down. Correct? If you pull the base away, the top will fall down. So if we look at this situation here, we have a right triangle. The hypotenuse is 13. Because the base is being pulled away from the wall, this distance is changing. So that is a variable value. And because as the base is being pulled away, the top is pulling down, that makes this a variable value. And we see an equation implied here because it's a right triangle. We have the Pythagorean theorem. So here's the question. How fast? By the way, when you see those words, how fast, your brain should say find the derivative with respect to time, because how fast is the rate of change, and it's related to time. So you know you're going to find d something dt. How fast is the top of the ladder falling when the base of the ladder is, let's say, 5 feet. Sorry, that's inches. Okay, it's 5 feet from the wall. That's a lot of stuff packed into that question. So let's decipher it. How fast? Hold it. Let's write find the time derivative of what? How fast is the top falling? Well, that would be this bit, right? So what's changing? The y value. Find how fast y is changing when the base is 5 feet from the wall. What will that be? That's this distance right here. So that's referring to x, when x equals 5. That's what you're being told to do. So I have my equation. I have a value of x to plug in, and we're going to solve for the derivative of y. There's something missing. Let's get started and I'll show you. We have x squared plus y squared equals 13. Derivative of x, but he's dependent on time. Derivative of y squared, but he's dependent on time, equals the derivative of 13, which is 0. Now, we're told that x is 5. Whoops. Sorry, plugging in what we know here. 2, 5, dx dt. What is dx dt? Well, the base of the ladder, we're told, is being pulled away. So that's how fast the x is changing, is 3 feet per second. So I'm going to go back and label this dx dt equals 3 feet per second plus 2y, and then dy dt is the thing that we're solving for, but we need to know what y is, and we're going to do that the same way that we did at the top of the page here. If x is 5, I made a mistake writing this down. It's 13 squared. There we go. Which is I can't remember, 169. Go back to the green. 169. This 25 from 169 is 144. So you see that if x is 5, y is 12. So we have 30 plus 24 times the thing we're solving for equals 0. 24 dy dt equals negative 30. Wait a second. How can that be negative? Are you okay with it being negative? Well, let's look at the situation. We're finding how fast the ladder is falling. We're finding the change in y. Isn't it going down? So y is getting smaller. It's decreasing. So your derivative would have to be negative, right? Finishing it up and reducing fractions to their lowest terms. We're going to get 30 divided by 24 is 5/4 feet negative per second. All right, cool beans, right? But let me ask a question. What if the ladder was 12 feet from the wall? That would mean the top is 5 feet, right? Because this is a 5, 12, 13 triangle. So I'm going to come up to the top here. What about when x equals 12 feet? Well, we have 2x, dx dt, plus 2y, dy dt, equals 0. 2x is 12, dx dt is 3, plus 2, y will be 5, dy dt, equals 0. So dy dt, when x is equal to 12 feet, is going to be 2 times 12 times 3, I'm lazy, give me a second, divided by 2 times 5, bang, bang. I'm going to get 36/5 feet per second. Holy cow. We had 5/4 down here. Change colors here so we can see the difference. 5/4, by the way, this is negative up here, right? 5/4 is 1.25, right? 1 1/4. 36/5 is going to be 7 point something, 0.2 feet per second. Holy crap. Do you see what that is? It seems like if the base is being pulled away at a steady rate, that the top would fall at a steady rate. But that's not the case. When it was only 5 feet from the wall, it was falling this fast. But when it was 12 feet from the wall, see how much faster it's moving? So the top is actually accelerating its fall. That's crazy and very interesting, I think. Next example. Let's say you have a situation where don't laugh at my pictures. I know you're going to laugh. Nope, already screwed it up. Don't laugh. Let's say you have the rope, you're on the dock, and you're pulling your don't laugh at my boat. You're pulling the rope. There's your water, right? This is water. Okay, let's say, do you see the right triangle here? You have this, and this, and this. This is going to be the length of the rope. This is how far the boat is from the dock. But because you're pulling the rope, the boat's going closer to the dock, right? What about this guy right here? Well, the height of the dock's not going to change. So let's say the dock, or the height of the rope where you're pulling it is, let's say, 5 feet above the water level. And you're pulling the rope, so this is 5. Pull rope at, let's say, 2 feet per second. So dr dt, because the length of the rope is changing at 2 feet per second, but the length of the rope is also getting shorter because you're pulling it towards you. So it's decreasing. That makes that negative. That means that the boat is moving, and I want you to find how fast the boat is moving. And I think we've already proven with the last problem that the boat's actually going to be speeding up. So how fast is the boat moving when it is 3 feet from the dock? So find dx dt when the boat is 3 feet from the dock. That means x equals 3 feet. We have the same situation. X squared plus y squared equals r squared. And we know that y is always 5. Good. So we take the derivative 2x, but x is changing in time, plus the derivative of 5 squared is 0. Derivative of r squared is 2r, but r is changing. Plug in what we know. 2 times 3. dx dt is what we're looking for. Equals 2r. dr dt, we're pulling the rope at negative 2 feet per second, but we have to find r. So we're going to plug in the 3 feet for the x to find r. So 3 squared, 5 squared, this is 34. So r is root 34, and that can't be reduced. Okay, dx dt, and this is for x equals 3, is going to be negative. 2's will cancel, and I'm going to get 68 over 3 feet per second. That's pretty fast. If you used x equals, say, 10, it would be going very slow. But the closer you get to the dock, the faster the boat is going to move. So you got to check it. Okay, a couple more examples. Let's say you're blowing up a balloon. Let's make this. I know this doesn't happen, but let's just pretend that our balloon is a perfect sphere. So I'm going to say spherical balloon is being blown up such that sorry, the volume of the balloon, in other words, how much air is inside it, is increasing at 100 cubic centimeters. I don't know if this is realistic. So you're blowing air in at a particular rate. Find the rate of increase of the radius of the balloon when the radius is 50 centimeters. Okay, we have to know some geometric formulas here. So the volume of a sphere is 4/3 pi r cubed. So we're told that the volume is increasing. In other words, the volume is changing with respect to time at 100 cubic centimeters per minute. Minute seems like a long time, but we're just going to go with it. What are we being asked to find? Find the rate, so that's going to be derivative with respect to time, of increase of the radius, so that's r, when the radius is 50 centimeters. So we have our formula to take the derivative of, and we have the values to plug in to solve for that derivative. So the derivative of volume with respect to time is, I'm just taking the derivative now, so r is the only variable here. We're going to bring down the 3 to multiply. It's going to cancel that guy. 4 pi, r is now squared, but r is changing with respect to time. So we have to chain rule that derivative. By the way, if you're talking about the surface area of the sphere, it's 4 pi r squared. So there's a direct relationship between how quickly the volume is changing and the surface area. Okay, let's take a second to talk. Think about a snowball. If you have a snowball, let's pretend it's a perfect sphere. Don't laugh at my sphere. Right, there's a radius. If that snowball is melting, it's not going to be melting from the inside out. It's going to be melting on its surface. So the bigger the snowball, the more surface area, the more quickly it's going to lose volume by melting. But the smaller it gets, the less surface area it gets, the rate of change of the volume of snow in the snowball is going to slow down, because it's going to slow down its rate of melting. Does that make sense? Think about it. If you've ever built a snowman on a snowy day, you know, in this area, you can be 3 feet of snow, well, 2 feet of snow, maybe 1 foot of snow, whatever, snow one day, and the next day it's 70 degrees outside, right? So if you've built a snowman or you've made big snowballs, they take forever to melt. I actually had to send my kid outside one day, I think he was like 7 years old, with a baseball bat, because it had been so many days that all the snow had melted and we still had that stupid snowman in the front yard, and it was going to kill the grass. So I actually sent my kid outside with a baseball bat to beat the crap out of the snowman, and he had the best day of his entire life. So, just saying. We've got the same kind of situation now, except in our problem, the volume of air in the balloon is increasing, so the radius is increasing. And once it gets to this spot right here at that size, how quickly is the radius increasing? That's the question. So, but about the snowball thing, the rate of change of volume, how quickly it's melting, is dependent on the surface area. You see that relationship? Okay, that's the end of my tangent. Let's go back to our problem. He had so much fun with that baseball bat. Here we go. dV dt is given as 100. 4 pi. R is given as 50. And we want to find the dr dt. So what we have is dr dt is equal to that 100 divided by 4 pi and 50 squared. And I leave that unmultiplied because I'm lazy, as you've probably figured out. So we have, I'm going to rewrite this bottom here as 50 times 50. Just so we can see how to cancel here. I've got a 4 that goes into 125 times. That becomes a 2 and cancels that. And I'm going to be left over with a 1 on the top and 100 pi on the bottom. That is a very tiny number, right? So, you know what we're going to do? We're going to try it again with a different value. What about when the radius is smaller? What about when the radius is only 10 centimeters? So then we've got the same derivative. dV dt is 100, 4 pi radius squared dr dt. I'm just plugging that in to this derivative right here, only the r is a 10 now. When I divide both sides, four pi 10 squared, I get dr dt is now 1 over 4 pi. Huge difference, right? 25 times faster than when it's out at 50 centimeters. So you can see that when the balloon is small, if you're pumping air into it at a steady rate, the radius is growing a lot faster than when the balloon is big. The volume is still changing at the same rate, but you've got more surface area, so the radius isn't changing as quickly. Cool beans. Okay, so you've got to practice this stuff. Do your homework. Remember, anytime you have questions, you can text me on the Hangouts app. You can send me pictures of your work. I can find your mistake or actually rework the problem and send back a picture. That is a really quick, easy way to get help when you're doing your homework, which I know everybody is doing all of their homework all the time. But you can also, if you really need individual sit down, take 10, 20 minutes, that kind of instruction, use the Hangouts app to contact me and we'll set up a time to get on Zoom. Please take advantage of the time that I'm offering you and don't ever struggle and don't get behind. The last day to withdraw and get a W instead of a letter grade is the 7th, which I think is next Tuesday, next Tuesday. So some of you might want to consider it. We still have 2 tests and a final, so there's plenty of chance to bring up your grades, but it's up to you whether you want to put in the work. It's going to get harder, not easier. So might want to consider that. Okay? Text me if you need me.